In this lesson, we continue to explore parametric statistical inference. In our previous lesson, we learned about the one-sample t-test and making inferences about a single population mean. Now we extend our understanding to the realm of two-sample t-tests and ANOVA. The two-sample t-test is a powerful tool in statistical analysis, particularly when we aim to compare means of two groups or treatments. It enables us to investigate whether there is a significant difference between the population means of these two groups or if it could be due to random chance. Like the one-sample t-test, this one is for an interval or ratio-level data. In a two-sample t-test, the null hypothesis typically states that there is no significant difference between the means of two populations or groups being compared. The means should be equal if nothing is going on here. The alternative hypothesis complements the null hypothesis and represents the possibility of a significant difference between the means. It is the hypothesis that researchers aim to support based on the analysis of the sampled data. Testing the null hypothesis in a two-sample t-test involves several steps to assess the statistical significance of the difference between the means of two populations or groups. To do this, we must compute a test statistic, which measures the difference between the sample means relative to the variability within and between the groups. In a two-sample t-test, the most commonly used test statistic is the t-statistic, which quantifies the difference in means while accounting for the standard deviation and sample sizes. Two-sample t-tests rely on several assumptions to ensure the validity of the test results. It is important to assess whether these assumptions hold before performing the analysis. The key assumptions for two-sample t-tests include that the observations in each sample should be independent of each other, that the populations or groups being compared should follow a normal distribution, and that the variances of the two populations or groups should be equal. The t-test is known to be fairly robust, meaning that it can still provide reasonably accurate results under certain departures from these assumptions, especially when the sample sizes are large. There are the three different formulas for computing the t-statistic in a two-sample t-test. Each has a different scenario depending on the data set. The independent groups t-test is used when comparing the means of two independent groups or populations. It assumes that the two groups are unrelated and have their own distinct variances. The pooled variance formula stems from an independent groups t-test and assumes that the variances of the two populations or groups being compared are equal. This formula is commonly used when the assumption of equal variances is satisfied. A quick assumption here is that this test can be used when the sample sizes are equal, as that can signal little variance between the groups. The separate variance formula is another form of the independent groups t-test which takes into account the separate variances of the two groups. This formula is especially useful when the assumption of equal variances is violated, or when we have reason to believe that the variances of the two populations are different. The dependent groups t-test or paired t-test is used when comparing the means of two related or dependent groups. This test is applicable when the observations in one group are paired or matched with the observations in the other group, such as before and after measurements on the same individuals. Let's look at an example of independent groups t-test. Here we have data from two groups on a cognitive test, and since subjects were placed in one group or the other, the groups are independent. Since the group sizes are not the same, they will likely have variance, and that requires us to use the separate variance formula test. The null hypothesis here is that the cognitive test score of the people in each group are equal. We can have StatCrunch do the calculations. Once we load in the data, we see that it is in two columns and ready for analysis here. Just click on the Stat tab, then T-Stats, then two-sample, then with data, and select the two groups to compare. The hypothesis default here can be left as is. The difference between the sample means should be 0 if the null hypothesis is true. Here we don't click on the pool variance as we don't have equal groups. Then click Compute. And StatCrunch will calculate the test statistic, give you the hypotheses it tested, and the p-value. The p-value is below 0.05 here, confirming our result is significant. We reject the null hypothesis. Can we do this calculation by hand as we did for the one-sample test formula in the last lesson? Well, If we look at the formula for two sample t-tests, we probably don't want to calculate these ourselves. And if we have just the summary data of the groups, we can just input that into StatCrunch by using the summary feature like we did the one sample test formula in the last lesson. Let's look at another example with a larger data set. We have it in an Excel sheet, Module 2's data set regarding birth weights. If we want to look at the birth weights of babies in the two groups of whether or not their mothers smoked, we first have to split the data into two columns and then run the two sample t-test. To have StatCrunch do the analysis, once we load in the data, we have to split the birth weight data into two columns by clicking on the Data tab, and then Arrange, then Split feature in StatCrunch to compare the two groups as it's all in one column in this dataset. Once we have the birth weight split by smoking status, we can do the test. We click on the Stat tab, then T-Stats, then To Sample, then With Data, and select the two groups we created to compare. The hypothesis default here can be left as is. The difference between the sample means should be 0 if the null hypothesis is true. Here we don't click on the pool variance as we don't have equal groups. Then click Compute. StatCrunch will calculate the test statistic, give you the hypotheses it tested, and the p-value. The p-value is below 0.05 here, confirming our result is significant. We reject the null hypothesis. Smoking does affect a baby's birth weight in this study. Recall from the last lesson our discussion of statistical power. We have the same considerations of power for the two-sample t-test. The goal of doing a power analysis for our test is needed to minimize the risk of a type 2 error. We can get this power analysis from our power table, where we see the minimum acceptable power level highlighted at 80%. As you see here and on the power table, there are 4 components to a proper power analysis to be certain you have enough subjects in your study to see the effect size you need to measure. The last test we need to cover in this lesson is the ANOVA test. ANOVA is used to analyze the differences between means of 3 or more groups or populations. In this test, we have one independent variable, also known as the factor, which consists of 3 or more categories or levels. These levels represent the different groups or treatments being compared. The independent variable could be any categorical or nominal variable, such as different dosage levels of a drug or various teaching methods in an educational study. The dependent variable, on the other hand, represents the outcome or response variable that is measured and compared across the groups. The dependent variable is typically continuous and measured on an interval or ratio scale. The null hypothesis in ANOVA states that there are no significant differences in the means of the groups or populations being compared. It suggests that any observed differences in the sample means are due to random variation or chance alone. The alternative hypothesis, on the contrary, proposes that there is at least one significant difference among the group means. As with our other tests, there are basic assumptions for running an ANOVA test. These include random sampling to assure independence of the measurements, normality of the data distribution, and the assumption that the variances of the dependent variable should be equal across the groups. The ANOVA analysis partitions the total variation observed in the dependent variable into 2 components: variation between the groups and variation within the groups. The F statistic is a crucial component of the ANOVA test. It assesses the statistical significance of differences among the means of 3 or more groups. Calculating the F statistic involves comparing the variability between the groups to the variability within the groups. An alternative way to portray the F statistic is in terms of the effect of the independent variable and the sampling error. This is done by defining the F ratio into 2 components, the effect of the independent variable and the amount of variation due to sampling error. The one-way ANOVA test is used to compare the means of 3 or more independent groups when we have one independent variable, also known as a factor, with 3 or more levels or categories. It allows us to determine whether there are any significant differences among the group means. The one-way ANOVA test is calculated by comparing the variation between the group means to the variation within the groups. First, the sum of squares is computed to quantify the total variability in the dependent variable. Next, the sum of squares is partitioned into the sum of squares between, representing the variation between the group means, and the sum of squares within, representing the variation within each group. Next, the mean squares are calculated by dividing the sum of squares between by the degrees of freedom within, and the sum of squares between by the degrees of freedom between. The F statistic is obtained by dividing the mean square between by the mean square within. Finally, the calculated F statistic is compared to the critical value from the distribution table to determine the statistical significance of the differences among the group means. ANOVA can be extended to situations with multiple independent variables through multi-factor ANOVA, the most typical being two-way ANOVA. You can also have repeated measures. ANOVA is used when the same participants are measured multiple times under different conditions. All these tests are summarized in our Guide to Tests document. Let's do an example of an ANOVA using data from a study on MGP supplement use. Here we have 3 diet groups of mice that were studied in low fat, and high fat with MGP. Fat cell diameter was measured in each group, which is our outcome, our dependent variable. Once we load in the data, we click on the Stat tab, then ANOVA, then one way is we have one independent variable here, the mice group. We select the separate columns we have in the StatCrunch sheet. Then click Compute and StatCrunch will calculate the test statistic and the p-value. The p-value is below 0.05 here, confirming our result is significant. We reject the null hypothesis. The supplement has an effect on fat cell size here. We can perform the same analysis on our data regarding infant birth weight, where this time the data under study, the weight in pounds of the mother or LWT is in one column, and our group to be analyzed is ethnicity. Parametric tests allow for precise estimation and hypothesis testing. By understanding their assumptions and limitations, we can leverage parametric tests to gain meaningful insights into populations and make informed decisions based on sampled data.